So today we're going to talk about regression. Regression is basically looking at some data points and trying to find a mathematical equation or model that would best represent the data points. So the first thing we're going to do whenever we do this is we're going to graph our data points. So we're going to just come over to Desmos. We're going to press the little plus key. We're going to go to table. And then we're going to type in our numbers. So I have 0, 1, 2, 3, 4, 5. And then the y values are 250, 330, 580, 800, 1650, and 3000. When I look at it, that looks like it's exponential. So if I were to connect our dots, it looks like it's exponential. So even before we do it, we're going to check it out. To check out if it is, we're going to type in our basic equations. So y1, and then instead of equals, we're going to do a little kind of like curvy thing. It's usually between above tab right next to 1. That just is kind of like, it's going to be approximately this. Exponential x is an exponent. So we're going to have a b to the power of x1. You need the subscripts because that tells it where to get the numbers from. And they're getting it from this table x1 and y1 up there. And if we look at that, it's a pretty decent model. It's going through 2 points exactly. It's kind of touching the edge of 2 points, and it's really close to the other 2. So that's good to kind of look at. So the regression type here would be exponential. My regression equation comes from down here. So usually this r squared here kind of tells us how good a model is. The closer to 1 is, the better it is usually. If it's closer to 0, most of the time it's not quite as good. So we're going to have y equals a is 157 point, when we're going around to the thousandths, 754, and then times 1 point. If I round that one, that's all going to become 0. So we're going to take 8 to the power of x. And then we want to predict the number of bacteria after 7 hours. So that just means if x is 7, what would be my y value? So I can just type x equals 7 down there and then see where they intersect. So I have to zoom out a little bit. And there you go. The bacteria value would be 9,657.35. So that's just taking 7 and plugging in where x is. And you could do that by hand as well. So you could rewrite everything and put that in there. Now, there are some limitations. Obviously, bacteria does grow and everything, but eventually it probably wouldn't be exponential forever. It would eventually have kind of a cutoff point, and you can't have usually like pieces of bacteria. It's a whole bacteria. So there are limitations to these models, but it kind of gives us an idea of where things are going. Okay, so if we look at our next one, we're going to do exactly the same thing. We're going to take our table and we're going to type it in. So I'm going to again start by pressing the plus sign, go down to table, and I just type in my value. So 1, 1.25, 1.5. I like to do all my x's first and then put the y values in as well. But you can do x and y values at the same time. You just have to be careful where you put them all. oops, 52.5 and 52.5. I'm going to press the little plus thing, zoom fit, so I can kind of see where it is. And I'm like, oh, look, looks like an upside down U. So that's going to be quadratic. I don't even have to kind of check it with anything. That's the only one that can be. We don't use absolute value unless that's the only option if it's multiple choice, because absolute value is like two straight lines, and life usually isn't like that. It's usually got more curves to it. For the regression equation, we're going to again do y1, our little curvy thing, and that's going to be ax. So we're doing our ax1 squared. We're doing our basic trinomial or quadratic plus ex1 plus c. Actually a really decent fit here. You can see it's going through touching pretty much every point except for that one up there. So this is a really, really nice fit. And our R squared value is again decent, so we know it's a really good fit here as well. There's our equation. So we're going to have y equals negative 18 x squared plus 58.5x plus 18.375. And then we're going to predict the volume with a side length of 2.5. So from our table, we know it should hopefully be about 58.5 if we have a decent model here. So I'm just going to put x equals 2.5 in. I'm going to figure out where they intersect. And kind of zoom in a little bit because there's 2 points there that are kind of really close together, which is good. So they intersect at 52.125. So a little bit off from where we would think it would be, but fairly close. And then they want a volume with a side length of 5. So I'm just going to change the 5.25 to 5. And zoom out so we can figure it out. And all of a sudden I realized that I might have an issue. And get negative 139.125. Now think about it for a second. Volume. We can't have negative volume, so this cannot happen. So whenever you do kind of like a regression problem or a word problem or a real life problem, you need to ask yourself, is this possible? And if it's not, you're not going to have a solution. Just like when we did some of our quadratics, we said we can't have negative time, can't have negative volume here. So that's something just to think about. And the reason for that is because this problem was taken from making a box out of a piece of paper. And papers are 9 by 11. So if you cut out 5 inches from each side, you don't have enough to cut out 5 inches on the 9-inch side. That's more paper than it calls for. Okay, last one. We've got the age of baby alligator in months and the length of the baby alligator in inches. We've got 0, 1, 4, 5, 6, 7. That's 22, 22.5, 23.5, 5, 6, 7.5, 28.5, and 29.5. Again, I can't see my dots. I'm just going to press a little zoom fit thing there. I look at it and I'm like, that's pretty much a straight line. So that's going to be probably more linear. It's got a little bit of a curve right there, but not really. So let's just check that out real quick. So y1 mx1 plus b. And again, that's a pretty decent fit right there. We can check some of the other ones. So we could do y1, ab power of x1. And the green line, you can see, really isn't that exponential. It's really kind of straight right there. So the blue line probably does a better job because you can see it's going to become more, it's going to be way steeper right there versus the blue line, which is kind of following the steepness right near the top. You could also do our quadratic and just check it out. So this is one way that you can kind of check out which one you think might work the best. I forgot the one. Definitely use the subscripts with these. So again, these are all pretty decent models just for that small section. But if you kind of look at it, when we zoom in, so that's our quadratic, and we can see that it's heading kind of some of our points to exact, and then kind of the pieces of a few. There's our linear, so I'm hitting 1, 2, 3 exact here, and then really, really, really close to quite a few. And then here's our exponential. This one's hitting 1, again, 2 exact, and then really close to quite a few. So our linear is probably hitting the most and going the closest to them and following the same kind of pattern with them. So that one definitely is our best one here. So it's linear. And our equation is going to be y equals 1.3. Oh, I forgot one. 1.137 x plus 21.583. And then when the alligator is 9 months old, so I'm just going to figure out, okay, when x is 9, what's the y value? And that's 31.815 inches long. So again, an alligator does grow for a long time, but it will probably eventually level out here and not keep growing in a linear fashion forever. Now you will have some practice to do on this tomorrow.